Hello, everybody. Good evening, good morning, and good day. My name is Tim. I am here to talk about spectrograms. I'm probably going to, yeah, no, actually, that is the actual word. And I am absolutely delighted that you have come and joined with me. If you haven't used this sort of streaming technology, the best thing to do is to add a comment, and I have actually got them off screen, and so I'll try and answer your questions as we go. And the other thing to note, though, if you do ask a question, is that there's often a significant delay up to about a minute, and sometimes I just get distracted, and I don't answer them as quickly as I should. So, if you're watching the recording, by the way, please do hit that subscribe button, because you'll be able to get first notifications for future events like this, and I am just absolutely delighted that we're able to uh, like spend some time like coding Rust. The first thing that I want to do, though, is actually like set out the scene about what we're actually doing. I have always kind of been really intrigued about like what these crazy diagrams here are. And one of the reasons why I'm really intrigued by what they are is because they're actually the input that all of the AI that deals with speech recognition or automatic translation goes through an intermediate step where they're translated into essentially into images, and then the machine learning algorithm feeds off of these spectrograms. And it's like, what? Like, why? I thought you were listening to sound, because and what's happening here essentially with like splatting out the sound data into two dimensions. But the really cool thing about the mathematics is that sound is just an amplitude. It's just a single dimensional variable over time. All we get or all the microphone receives is uh, a hint, like an intensity at a particular time, and that intensity, well, is sampled, let's say, at 160 kilohertz, and so the 160,000 times per second, and then we can use mathematics, a Fourier transform, to actually pull that apart and try to say like which of the harmonics are actually responsible for generating the amplitude that we actually find. And so I'm going to do a bad job at explaining the mathematics, but hopefully an okay job at explaining the Rust. If you know a little bit about the mathematical background, then please contribute with your views, or additions. And good evening. I know that we've got someone here in the UK, Conrad, and it's nice to see JD there as well in the evening. We're not going to spend, hopefully, this won't be a very large amount of time, maybe 35 to 45 minutes. Hopefully, I can get through it. I just have this tiny tendency where I get distracted and don't finish the command that I set out to. So, in our case, we are going to create a little spectrograph app, and it's going to take a wave file and then generate an image. Now I've got one called I've already got I've got a cheat sheet. So I've got an implementation that we'll walk through, and but I'm going to hold this off to the side and then start fresh. So the so where should we start? We'll start in main. So the thing that I've just done, I've got this spec app, and I'm using Cargo, which is just a command line utility for being able to interact with the Rust compiler. And I can sort of immediately run the code or compile, and this took less than a second. We now we'll start by let's reading in from the file system. So probably not the best place to start, but it's an okay place to start. I can call on a static method or actually a function within the standard env module, which will return me an iterator across the args, like the argv array provided by libc. Now, that isn't actually enough because I want to do things like ask for, in my case, the first item that, well, actually, we could just say what we want is just one thing, but I want to show you how to take those arguments and to kind of collect them into a vector, which means that you'll be able to go and ask for the fourth element at some point in the future. And in our case, we're going to say args get 1. And then if it's not there, we will say no file. Essentially, we've just added a little bit of work, a little bit of machinery or some smarts to our code, and unused variable path. That's okay. The -q quietens things, but it doesn't silence warnings. And we actually get a panic, and the no file message is what we wanted to see. And so now I'm going to have to provide a file by providing -- and just say parrots.wave, which actually is in the directory below it. So now it doesn't actually check that there's a file there, but we can get to that. I almost feel like pulling this out and revealing it piece by piece rather than just wondering about the best way to do it. Sorry, how is everyone? I'm going to go check. Do you mind? Sorry, what I meant to be, sorry, I got a question here. Your video is covering the code. Can you move? Yes, I can move. Sorry. And then again, can you bring a video down? Sorry, I meant to do that earlier. Apologies for being in the way. And where were we? I was just opening up one thing over here. New window. Sorry, I'm just playing off screen. I'm just checking that everyone is happy. There's no other questions. How is everyone, by the way? Does anyone do digital signal processing for work? Or for pleasure, let's say? I suppose a whole bunch of people are actually watching this on their phones, so they can't actually read any code. And I will be with you very, very shortly. I just one thing that I had done in preparation for this hasn't quite worked, and I'm flapping very, very silently, and I think I'm just going to have to bypass my plan B and stick to plan A. Aha, cool. Okay, now let's. I found something, which is kind of the intermediate phase where I want it to be. Okay, apologies for that. I'll stop flapping. I'll edit that out in the recording, so You won't have to launch me again. Let's talk about sounds. Now, the way that we're going to read in sounds is with a library called Hound. Now, what is Hound? Well, go to crates.io, creates Hound, and then from there we can we get this quite mature library. It's at version 3.5, and to ask for it to be included into a package, we add it as a dependency, and we're going to say we want version 3.5. And now I should be able to have some reader thing. So I've got a path to a file, and there's my path, and I've got a wave reader from Hound. I open and then I unwrap. I'm going to change this to expect and say I was not a valid wave file. So just in case you've never really thought about what's actually inside a wave, you've probably seen MP3s or like MP anything and a whole bunch of other sound formats. A wave file is uncompressed, and that just avoids one step of the processing pipeline where we need to say take an MP3 and decompress it into essentially a wave and then go from there. So we're sort of bypassing that step, and now I want to sample from the file. And so we've got a really large design space here, and well, actually no, this is in terms of we can take samples from the file, and then I am providing sort of a conversion. Well, I've got there is a read process which itself is fail, so it also returns a result, and then there is another way to do this, which means that we could essentially skip any samples that were broken. So I could sort of initialize for mute. By the way, I can also skip I can also skip a bunch of the boring, or not necessarily boring, but the more elementary Rust stuff if people would prefer. So, but I thought that it might be worthwhile sort of explaining what's happening as I go, rather than just kind of overloading you with some text. Immediately I get into some quite advanced syntax with type hints in line. So we are going to so this reader thing returns a sample, and it might be a sample. It's a result, and I'm a little bit confused because normally Rust Analyzer would help me out here. I could do this by doing that. Hopefully we'll get some help from Rust Analyzer. And the sample is a result, and so I need to kind of like extract out. And what I'm going to do is say that I'm going to match on sample and say, well, if you're okay, like if you are like a successful read, then I'm just going to do nothing. Now it's going to get confusing because I'm going to shadow a few variables and in multiple places. So we've got, actually, I'm going to say read. So I'm going to match on sample result. Keep it as simple as possible, Tim. Okay, sure. Okay, sample result. Then I'm going to match on this and say, well, okay, inside here is a real sample. Okay, return that as F32. So we're going to need to do some mathematics. We're currently pulling things out as an integer because that's how we we can go and have a look at how the audio is actually encoded, but do you remember right at the start I said it's an intensity. The microphone takes sound waves, like physical waves, and it vibrates a sensor, and the intensity of that sensor will increase the amount of sound at that the value of this sample at that specific time. Now, if you are recording at 160 kilohertz, there is 160,000 samples in every second. And if there's an error, and we don't actually need to know anything about what's happening, I'm just going to skip that frame. Now, this is probably a terrible thing to do, but for live streaming or for some things where actually your processing step just kind of needs to continue, skipping a frame that became corrupted is actually what you need to do. So one of the cool things, if you ever get into this field, is that some of the file formats that are designed for broadcast, like Netflix, for example, will actually have some really clever information theory behind them to be able to reconstruct a frame if what the occasional one doesn't make it all the way through. But over TCP, that isn't a problem, but TCP is often too slow. So yeah, it comes really, I'm losing myself. So now we have a sample. Yay, a sample that is of type. So this sample here is of type F32. And now we want to push it into our samples vector. So that is a less idiomatic way of doing the line. Currently, lines 10 through 12 is a very functional style. It's very declarative. There's no control flow essentially, but and it is also idiomatic Rust, but it's a little bit more intimidating if you haven't used Rust before. The code that is currently between 15 and 23 is a little bit longer. I do one thing differently, which is that I'm not unwrapping. I could have unwrapped it if I wanted to, but potentially simpler for people that are from a more imperative background. Now, we've got some decisions to make around how we translate our samples into bins. Now, we're going to apply a Fourier transform, which is going to take some range of samples in one dimension and then split that out into two dimensions. And the way that we need to do this is through a windowing process where, let's say for, we're going to pull out a 1,000 frames, and then we're going to just do an analysis over, or like a 10 to the 2 to the 6, right? Or is it? And we're going to actually apply the Fourier transform for a given frame based on its friends. Now, the problem with the Fourier transform when we do this windowing, which is like splitting the original samples into fixed size widths, which are about maybe 10 milliseconds or 20 milliseconds in size, there are zeros right at the end. And the mathematics don't really like that. And so we need to apply a secondary step for being able to kind of merge two Fourier transforms over one another. So there's a bit of an overlap where, and we'll say that it's frame size divided by 2, just for now. We want to do our fast Fourier transformation, and so we're going to need Rust FFT. And Rust FFT is over here. And we will take the version 6, let's say, and bring it into local scope. So Rust FFT, and we're bringing in a trait. Traits and types look extremely similar when you're bringing them in from external sources, but this FFT thing is actually a trait. It sort of extends a few. By bringing the external trait into our local scope, we gain access to methods that have already been implemented in the library for types that we have available to us, like, for example, our vector. We also need a direction. And I want to bring in another helper, which is a particular algorithm for having a for calculating a Fourier transform, and I will allow the people who really want to look this up, they can go and dig into what a radix 4 does. So I am pretty close to being able to build it. So I've got FFT here, which is an instance of the radix 4 algorithm that uses a frame size, which is a slightly different sense of the word frame. It's not an audio frame, although it will be anyway. And we're going in the forward direction, which means a lot to people that know a lot about the mathematics. And now we are going to create an image at the same time. So what we want to do is we are converting a amplitude into a spectrum and an intensity at multiple points. It's quite difficult for me to kind of explain what's happening, but allow me to try my best. A Fourier transform is sort of the intuition would be that very complex functions, let's say the amplitude of an audio signal over time, could be approximated with multiple combinations or linear combinations of the intensities of sine waves. And I'm going to do this quite bad. Oh, I've got some questions about before. Just isn't the unwrap on line 12 different to how error is handled? Yes, it is. So this error unwrap would be the equivalent to me taking sample result. Sample result unwrap. So if I had done that, the two algorithms would be the same. So sorry for the delay. Okay, so we are essentially summing up sine waves now, but we don't have access to the actual sine waves. We've only got the output from the sine waves, so we kind of need to guess what the most likely sine waves are in combination to generate the thing that we found, and the and there are analytical ways to calculate this, and um, and there are probably Bayesian ways to do it as well. Or like we could use statistical methods, or we could use analytical methods, and I'm not going to try to regurgitate a whole bunch of old mathematics that I used to know. Apart from the fact that we've now bumped into some more rust. So I have my samples. So samples are timestamps, or at a particular time, how much was the microphone like vibrating? What was the intensity that the microphone was had at that time? Now, then frame size is the number of frames that I'm going to use to calculate the configuration of sine waves at that particular point, and then we're going to have an overlap whereby we're going to use some information from the previous call and the future call to sort of smush or smooth out the problems that occur with the discontinuous, with the fact that mathematics doesn't really like zeros just being everywhere. And if we were to avoid the overlap and just go frame hard to frame, it would be like as if there was no information passed from the previous time step to the future, which would mean that you would get these really horrible black marks in the like in the output. It's probably a really bad analogy. But I just think of like now this is all modeled, so you actually have the ability to go and tweak the output and see how it changes. So one of the cool things about writing this yourself is like you get to figure out, like, we can go and delete this and see what the change actually is. And I think now let's do that. That sounds kind of cool. Now, I've got a whole bunch of mathematics that I'm just going to copy across. Now, actually, maybe I won't. So I'll try to. I've got a bunch of constants in here, and the mathematics are such that these are the right numbers to use. So we are going through, every window. I like this quote, by the way. So thanks very much. As you begin to walk on the way appears. I like it. So that's sort of saying that, at the moment it's unclear, but as you progress, it'll become more obvious. At least that was my interpretation very quickly. So we have a whole bunch of crazy constants. I assume that the mathematicians that figured this out know what they're talking about, and I'm just going to leave it there. We're creating a number within the complex frame, sorry, on the complex plane, and we're doing this by repeatedly iterating over every frame. And a frame is a part of like one particular audio sample, and so you could imagine that every sample gets it gets analyzed multiple times, but its position in the algorithm changes, because we can see that we do multiply j, which is the position at which the frame is in its family of frames, and the family size is in this case 1024. I'm not sure what the trigonometry and so forth is doing, but I presume that's a smoothing curve. Anyway, we now we now call something which so apologies if this was unsatisfying. You'd like a really analytical, a really nice answer. Unfortunately, I don't really have that for you. I can, however, give you how to calculate the Fourier transform, which is process. So we have a frame over here is just a big row of numbers, and then the Fourier algorithm. Oh, and we frame here on line 34 is a is what we have. Gosh, so I'm using the same variable name in two places. So I'm just going to call this frame 2 just to. So frame is the samples, and frame 2 is the samples after some transformation step that involves the position of the frame inside, the position of the sample within the frame, which is a collection of 1,000 samples. Gosh, sorry about all this. This is nonsense. We are actually going to do something fun really, really soon. What I need to do is also create an image. So we're very, very close. So we've now got a Fourier transform for our frame, and now we need to plot it. And so to do so, I'm going to need to bring in a new crate. And which version? I think it's 0 from memory. It's 0.24. And this will give me a sort of a buffer, which I can write numbers into. And those numbers, and it also knows how to save that as a PNG, which will be quite useful for me because I'm creating a command line utility which is going to write image files. And that's good. Okay, so from here, I now need to go through my Fourier transform, which has intensities at multiple places, and then translate those to pixels. Now, allow me to show you the iteration process. I'm going to do it by copying and pasting rather than wasting your time further and making you watch me type. So J is a different J. So we're going across frame a second time, and we're going across the original frame. No, we're not. We're going over frame 2. Because frame 2 was what we actually applied the Fourier transform to. And then we've got image width, which I haven't defined yet, but I will get to that. And then I have some value, and we need to apply a little bit of normalization to actually make it look good. So humans are strange in that their perception of color and intensity is not linear. And that is, if you double the light, if you double the amount of light on a surface, you're not going to have people looking at the surface and say, oh, it's twice as bright. That's not how human cognition works. And so we're going to normalize, and that's different normalization. But what this means is we're going to take the range, we're going to suck it down to 0 and 1, then move it down to unit scale. And what else am I going to do? I'm going to apply a log. Actually, let's just keep things linear. For now, I'm going to convert this into a U8. So I can then say that it's a pixel. So, oh gosh. So this is going to be a pixel on a picture. And this shouldn't actually need... Oh, I know. Yep, this doesn't need that. Yep. So I got magnitude, magnitude, magnitude. Now I don't have an image yet, and let's fix that. Okay, so image buffer. Down here, when I do FFT, you can put this wherever you want. I will define image width and image height as some function of the frame size. That is that's going to cause us problems because the frame size we're hard coding. It's not actually dependent on the the length of the audio that we've got, and so this would need to be changed to make it more general purpose. It's not as hard as you might think to do. We could, for example, say that the width is the length of samples, I think, divided by frame. Yeah, let's go with this because I know that it produces an output that's kind of sort of okay, and then you can continue to tinker. I don't know if anyone has ever tried to like write their own shader. You start and it's like, wow, isn't this amazing? And then you realize, oh boy, I've got a lot to learn to make a decent shader. This is the reason why people spend their whole careers doing this one particular thing that I could learn essentially in an afternoon. And I would like standard path, and I'm going to sort of say unwrap the... Now I'm bound to get a whole bunch of cargo build errors, and okay, so how about what have I done here? Oh, I see. Cargo.toml. I am just going to push in star for the moment, and the reason why and then while it's compiling, I'm going to go check what the actual version is with the browser, and then we'll fix that for later. Maybe it's not the image crate. Let me check. Ah, it's the wrong library. And I do have a typo in there, so which it detected, which was something around this crazy syntax that I had described earlier. Where I had provided the type hint for samples, but I hadn't actually called the method. Okay, let's check the questions because this is a good time for answering some, because compiling isn't amazingly interesting. I don't know if you've encountered that yourself. How is everyone doing? I will just maybe do a very small plug for various social channels that I've got. Like a good place to find me online is YouTube. I've been trying to really increase the frequency of what I've been publishing or producing, as well as gradually increasing the quality. I've made a couple of mistakes And I've tried things, and but now I've got a binary. As I've made mistakes, and but in general, I think that uh, in general, he says, I think that people are really enjoying the content that I've produced. Now, oh, we've got an error. And I left this one in because I didn't want it distract from the the code that I was explaining before. What's happened here is we had we had this problem whereby the audio is some is arbitrary length, but we've got a fixed frame size, and that's a problem because we're going to hit out of bounds problem, like out of bounds area. So if I is larger than the height. The other thing is that this Fourier transform is going and checking as in frequencies which we might have recorded but are outside of, like, because it's a wave file, so it isn't specialized for frequencies of human of like human speech. And so at least that, I think that's right. And so I don't actually know where the top of a wave file is. And so if I is image, my code is now getting longer. Can I move anything to the right? You know, I can, but I might move me. I can move me. There we go. Let's move me this way. Oh, it didn't save. I'm just going to actually, you know what? I'm sorry for playing around with this. I'm going to, it doesn't like changes like this during a stream. Save. Did this save? Update. Okay, so now I'm little. Oh, and the question is, will the code be available on GitHub? Yes, it actually is. I was going to publish it before I went live, but I thought I might make some tweaks while I go through. So yes, it will be. If you go and check the description tomorrow, come back to the video, you will see that the description has been updated, and there'll be a link to the GitHub page. So the general GitHub page to go to, by the way, is Tim Clicks, GitHub Tim Clicks tutorials. And I'll post it into this repository here. So the so that will be the best place to find it. Okay, cool. We're getting so close to an image now, he says, with like fingers crossed. If I is image height, then we do something, we continue. We essentially skip. We could actually break here because we're only getting higher, so it's only getting high. We also need to do a similar thing when we get to the width. We have only got so many. Yeah. So if J, width is the time. So this is along the x-axis of the actual plot. And if J is greater than or equal to image width, again, once you're doing this yourself, you'll be able to tweak this so that your image is a function of the actual wave, like of the actual input. We break. Okay, so now we shouldn't. Oh, need to compile the thing again. It shouldn't take too long this time because we made minor change. Aha! And like, what? There is our ugly picture. It's like, hey, whoa, 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 whoa. You promised me a nice photo. Okay, so I've got a couple of things that I need to show you. And so first of all, do you remember how I said one of the things that we should do is we should apply a log transformation? And I think I said that. And what we're looking for is I've got some birds. You won't probably want to hear this. Oh, I think I've got some birds screeching. And the other thing that we're going to do is start with black, and then hopefully so do you remember what I said about cognition, that humans see lightness and darkness very differently. And so in this diagram, it's really hard to detect where the black pixels are, partially because human speech is in a very narrow band, and we actually are going to use a log transformer to kind of like stretch out the human speech, or the things that are audible, the parts of the speech that is audible to humans. And we're going to change the colors so that we can see things. So now you can see that parrots are screeching at this time point in a actually, you know what I should have done? I should have started with complaining about YouTube's like the compression algorithm while you're doing a live stream is such that like it's always going to look terrible. But now you may notice that this black smudge looks very, very different to anything that you've seen. Allow me to go back to, I think I had an image search before, and you immediately notice that there is like quite a huge differences. So one of the things that they are applying is they are using there's actually this is the default spectrum in MATLAB. It's a thing called JET. It's a really bad, like this, using red for intense values, and I'm simply using the magnitude that I get from my Fourier transform and just saying that that is red, the red, blue. But they're actually doing something else. They are taking this linear step, and then they are going to try to and then they're trying to like push that on like the visual, like they create a line in color space where 0 means something, and it means let's say blue, and on the other side of the color space is red. Now there are other ones. There's a much more scientifically robust one, this that Python now uses, or a library called Seaborn called Veritas, and it maps between this light yellow color and a really deep purple. This enables humans to perceive similar changes in intensity in a similar way visually as what's actually happening in your brain. But that's actually all next steps. Being able to get this far and have an actual picture from a sound wave is, I think, a really cool step. And I really encourage you to kind of like lose. I want to try. I've just thought of one other thing to play around with while we get into this. What I was thinking of was like, well, why don't we store the last values that we had, and then have the color change, or maybe the redness of the color, maybe when you are very different from your previous pixel or previous. I'm going to try and make a really quick change. I can just see some dust specks. Well, no, this is not dust. This is a parrot squawking. This is like this is a miracle of nature. At least that's what I'm trying to convince myself. Magnitude. So I wanted to say last is actually it's just a 0, and then if so we'll just say that the red is 250 is the difference between, so we would yeah, let's just say it's the difference. So magnitude minus last, and then this will look horrible right on the side because the very first value is 0, but hopefully you'll forgive me. This is going to look very yuck, but hopefully interesting. And now we need to reassign last equals magnitude. So you can obviously build visualizations that don't exist in any scientific literature. And because our pixels here are very distinct from one another, they change very rapidly. There are some grays and things in here, but there's in this section over here where my cursor now is, you can see that we've got some sort of medium reds. We're only changing that red one. If we want more pixels, by the way, we can change this. So let's change this to, let's give ourselves some more resolution and make, or at least larger frames. And let's see what larger frames does. So we can build again and reapply. Wow, okay, so now we've got way more, many more pixels. So it's all very spread out. And it's only a 2-second audio frame, but now the samples are even further apart, so there's a big difference. I should stop playing. Could this underflow or something? Yeah, there are a whole bunch of numerical problems that can happen if you don't know what the parameters are doing. Like we've arbitrarily say that the frame size is divided by like 2, but let's try and see what happens if we have a very small overlap and see whether or not the Fourier transform now has significantly less data to work with and what it actually produces as output. And because one of the things that I asserted really early on was that the Fourier transform is very sensitive to a bunch of parameters. And you can see here that the whole visualization is different. So you kind of get this bloody column, which is kind of weird to think about. And they say, well, what is the actual accurate way to go from sound to an image? Well, unfortunately, there is no perfect way. It is completely up to the conventions of the scientific community, and there will be established standards. In the machine learning community, they have said that all input to the machine learning algorithms essentially needs to be 16 kilohertz. So you downsample your audio all the way down to 16 kilohertz. And I assume that the spaces with that this binning is applied is all standardized. However, I say that I hope that it is, but I bet that different learning algorithms have been trained on different features, and that's like this sort of feature engineering is kind of a problem. So what happens if we have essentially, what is another parameter that we said? We stepped by overlap. The other thing we had, we've got all of these constants. Now we could muck around with those. I don't know what the significance of this trigonometry is, but let's find out. Like I've got now I would like to try changing some of the other colors as well. We've got red, green, and blue, but what I'm doing is I'm really mucking around and mucking up the maths. This doesn't have anything obvious to me yet, but I haven't actually run the thing. So yeah, we start to see that changing the parameters of the transform definitely has an input, has an impact on what is actually produced. And I did wonder what this cos term did. So how about we just remove that and we'll find out what actually happens. How did you find these constants? I'm embarrassed to say that it was actually ChatGPT that that told me about the constants, and in fact drew me a nice LaTeX diagram of the equation. So I will actually share that conversation with you because I think that would be useful for transparency. So again, that'll be one of the other resources that are available in the chat. In the description. So now we've removed this cos parameter, and the Fourier transform is like essentially, I mean, I don't know if this is meaningless, but at least before we had some structure, and now it's just all over the place. So yeah, okay, so this is the end, by the way. I will just hit 10 o'clock where I am. I hope that you've had a really wonderful time hanging out. Please do the like thing or the subscribe thing. The recording will be there. I'll also post an edited version, which is slightly more cleaned up, hopefully. About this time next week is what I'm aiming for. And until the next time I see you online, I hope that you're doing well. And please feel free to send through any comments in terms of suggestions, feedback. Very happy to listen. And also just the tiniest shout out to something that's happening over the weekend. I'm doing a 4-hour marathon stream where I'm going to go through as much of the Rust language as possible in that 4-hour period. I'm going to try and see if I can run every example from Rust by example in 240 minutes, and that'll be lots of fun. Hey, thanks very much, JD. It's been a real pleasure, and thanks very much for sticking by. And I will, and everybody else, and I will. I'll see you. Oh, yeah, I'll see you later. Take care. Bye bye.